Oh, good afternoon. We are the team number 6 and is formed by Eric Niñan, Alejandro Sánchez, and Marco Quiroga. So, problem that we're going to explain is the number 2 that is going to be this transfer function. So, we're going to explain every point of this document. So, can begin. Result of all, it says that we have to design a compensator that doesn't have a steady state error and a stabilization time of 2% of 0.5 seconds and a damping constant of 1 of divided of the root of 2. So we know we have the constant the document gave us. This our transfer function. We just multiply 3 in the numerator and the denominator just to simplify the transfer function. So this is the transfer function that we're going to use in this example. So with the constants that we know already, we are going to calculate the sigma. So as we know that the stabilization time is 0.5 seconds, so the sigma will be 8. With the 8, we just calculate the after we calculate the sigma, we pass to calculate the theta. So with the damping constant that we have, it is equals to 1 over the root of 2. As we know, the damping constant also is equals to the sin of theta, and for this we clear the theta, so the sin inverse of this value is going to be equals to 45. So we just already have these two values. After this we can draw the values to calculate the omega t. So we know that omega t is equals to omega n and cosine of theta. Also we know that the tan of theta is equals to sigma over omega t. We can clear the omega t here and calculate this value with the two values that we already calculate. So we got that omega t is equals to 8. Well, after we have these values, we just can calculate we can draw the poles and the sigma omega t in the axis. So as we know, we have here two poles, one in the origin and one in -3. So here is 1, here is 2, and we're going to look for to reach like the pocket ball of a round locus. So we can build two different compensators. So one type is PD or PED. In this case, we're going to do a PD compensator that is going to be just to add 1 0 in the x negative axis. So in this case we put the 0 of the compensator right here, and we can pass to calculate the exactly position of this zero. If we if we can put or we can build a PED compensator, we just have two zeros and one pole in the region, but we saw that this compensator is easier and I don't know, less complex for between the other compensator that is the PED. So, well, first of all, we calculate that the angle, the exactly angle from the zero to the point that we already know that this point is equals to between the sigma and the omega d, that is -8 in the negative axis and 8 in the imagine axis, that is the omega t. So this point we already know, and we know that the real angle minus all the temperature angle is going to be equals to 180. So we calculate first the temperature angles. So, well, after we calculate them, that is clear that this one is right here, is going to be like this point. So we know that this angle is 45. So the distance, the angle between this point and this point is 90 degrees plus 45 degrees. So right here is this angle, and the distance, the angle, sorry, for this point to this point is going to be equal to 90 plus this angle, the extra angle right here. So after we calculate this, we can know that the angle between the x-axis and the point from the zero is going to be equals to 77. So as this angle is lower than 90, we know with this we can know that the zero is going to be left of the sigma, sorry. So we put this zero right here. After we calculate this angle, we can pass to calculate the distance of the zero and the origin. We already know the distance between the sigma and the origin. That is 8. So we put right here this triangle, and we pass to calculate with this angle. We pass to calculate the distance between sigma and zero. So right here we can see the distance that we got, that is 1.47, and we just add to the 8 of the sigma and the region. That is going to be 90.47. Already that we gave us this value, we can multiply the compensator to the system, the plant of our system, with this condition that we know that always we have to do for the compensator. The result of the multiplication of these two, we are going to value the result in the point that we already know, just to calculate the constants of our compensator. Or after we put the point evaluate a point in every s that we had in the result. Well, we just this result we also put that equals to 1. So we put the denominator as a magnitude that, well, you guys can see this calculation over here. We calculated the magnitude of this value and pass to the right side, and the magnitude of this value and pass to the right side also, but this value we are going to divide the numerator. Is going to be equals this value between this value, just the magnitude of both of them. We can see right here. So the key are going to be equals to 0.53, as you guys can see right here. Well, as we know, we have right here the value of k and the value of c1. So as a formula, we know that a PD compensator had this formula, and we clear some values. Right here we can see that key is going to be equals to kp and td right here, and c1 is going to be equals to 1 over td. We clear the td because we know the c1 right here, and we calculate. We got the value of td that is going to be 3.105, and after this we calculate the kp is going to be equals to 5.1. Well, after all we got this constant, we just can put in the formula to see the compensator. Well, this another point. There is going to be this ask us to perform a per filter. This is the compensator that we got. There is the kp that plus td is equals to 5.1, and the value of 1 over td is equals to 90.47. So, well, here we just left to multiply the td. Here's just a kp. So right here must be this value, the 0.53, the whole key, not just the kp. So here is not 5.1, is 0.53. So this compensator, the correct values is 0.53 right here plus s minus 94.47. So we can simulate the closed loop of this system, or just this system, so we can verify the approximate value of this result. So we go to MATLAB, where I have already the program. So here this one is our plan of the system. Here this one is the compensator, the values that it doesn't have a denominator. I already have just one, and we can just await this value. So we have the transfer function of the plan, the transfer function of the compensator, this both, and we multiply both of them and give them a feedback of 1, just to give them open loop. Well, we step this value to see or step response of the system with the compensator, so we can see how stabilize in point 0.5 seconds more or less, as the problem gave us right here. We can see all our step response try to reach or stabilize after this time. Well, we can wrap the air locus of our system right here. We can see the 0 and the 2 poles, -3, 8. Well, this value is more or less -10. The sigma is right here. This is -8. These points we already know. We have the roll locus right here. So it seems just fine, the Pokeball. Well, we know we have this prefilter. Well, the prefilter is just to eliminate the effect of the pole, of the 0 that we add with the compensator. So we can simulate to verify the performance parameters of the compensator before. So well, to verify the prefilter that we assign, we're going to simulate using the space model and the closed loop system with the control rule. But you guys going to see, this is the prefilter. You guys going to see the whole simulation after we explain the state space model. So we can pass to a state space model. So this is our plan. We have array here, and we just pass the input, that is the x of s, multiplying the 24, and this denominator to multiply the I of this. So we have right here, and we pass to a time with a plus inverse of this, and we have this value right here, and pass the we clear the g of t of 2 prime, and we pass the -3 gdt prime. So we have this function, and we can pass to the state space. We can pass to a state space model. That's you can see. You guys can see that here is the GT prime and G2 prime. So this is going to be our A, that GT prime is going to be 0 because 0 and 1, because it's going to multiply, is going to be equal to G of t prime to G1 prime. To G of t2 prime is going to be equals, as we have here, -3 G of prime. Okay, we here put 0 -3. -3 is going to multiply this one, and 0 is going to be equals. We just to formulate this function right here, and are going to put our input right here. We have to put 24 as our function. Well, after we calculate the state space model of our transfer function, we pass to verify the observability and controllability of the state space model that we already calculate. So, to the controllability, we calculate the alpha that is equals B, the matrix B, concatenate the matrix AB. So we already have this value, this matrix, and we calculate A by B. A by B is going to be equals to this matrix by this matrix, A and B. So to calculate this multiplication, we have this matrix 2 by 2 and this matrix 2 by 1. So we already know that we have as a result as a matrix that is going to be 2 by 1. So to calculate this position, this number, we multiply the rows or the columns. So 0 by 0 plus 1 by 24 is equals to 24, and this position 0 by 0 and plus minus 3 by 24 is going to be equals minus 72, as the determinant is equal well, with this value we concatenate the value of matrix B and this value, so we have this whole matrix. So as we calculate the determinant of this value of the alpha, and we know that the determinant is going to be minus something, but is different than 0, it is going to be control. This transfer function state space model is going to be controllable. So we pass to if the state space model is observable, and we know that beta is equals to the matrix C, concatenate the matrix C by A. So where we have the matrix C and is 1 0 this side, and we calculate the matrix A, the matrix C and the matrix A, as this matrix is 1 by 2, in this matrix 2 by 2, we know that these matrices are going to be 1 by 2. So to calculate this matrix, we do rows by columns. So by this position, this is going to be 1 by 0 and 0 by 0, 0, and 1 by 1 is 1, plus 0 by minus 5 is 1, is 0. So it's going to be 1 in this position. We concatenate this matrix, and we know that the determinant is of beta is going to be equal. So is going to equals to 1. So the determinant is of this matrix of beta is different than 0. So we know that the state space model is controllable and observable. After this, we are going to obtain a control rule for the state space model that will have the same performance of parameters that we already have in the point 1. So we have this formula. This formula is going to be equals to our point, and we're going to have to calculate inside of the determinant of this matrix. So S plus the identity is going to be this matrix, minus A that we already have plus P, a matrix 2 by 1, and K, a matrix 1 by 2. Well, first we do this calculation that is going to be this equals to this matrix, and this calculation that is going to be this matrix. So we do this calculation and is equals to this matrix, and we do the determinant of this one is going to be equals to all of this, all of this s square. Well, we after we calculate the determinant of this matrix, we're going to, as we have equals the point that we already know in the point 1, so we're going to clear to obtain the K1 and K2. So we do the general formula we use to calculate or separate the real numbers and the negative numbers. So with the general formula and this equation, we use to get the real number that is this one, and the imaginary numbers that is going to be this one. So we are going to separate them. This part in this one equals to this one. At this point, the point has two real number and imaginary number. So we match this part to the -8 and get the value of K2, this number. So with this number we assign them in this formula that is the imaginary part. So after this, we're going to obtain the value of K1 that is going to be equals to 5.33. So this is it, and we pass to the last part of the activity, that is the simulate the closed loop system with a control rule of 5, including the required pre-amplifier that we designed. So we pass to MATLAB, we already have here, and you guys can see that the control rule already are function in MATLAB to calculate this control rule. So we assign the all four matrix that we use, A, B, and C, with the results in the state space model that we got. So here we have this -3. Sorry, right here is -3, and I see this or prefilter and or point to calculate the values of K, and we run the step response, and we can obtain this value and see a clear step response of our system. So that's all that can of the activity. Thank you for watching.